Thanks. So hi everyone, my name is Jerry Xuan. I'm a grad student at Caltech, and today I'll be talking to you about the atmospheric composition of a cloudy brown dwarf companion from high and low resolution spectroscopy. I'd like to thank the organizers for organizing this great workshop, as well as my advisors and collaborators who helped me during this process. So unlike, sorry. Yeah, okay. Yeah, so unlike the previous talk, we're looking at direct imaging as well, but of objects that do not explode. So these are giant planets and brown dwarf companions. Over the past 20 years or so, direct imaging surveys of these objects have detected dozens of these objects with this range of masses and, roughly speaking, this range of separations from their host stars. So these objects are technically challenging to image because they are much fainter than their stars, on the order of which are on the order of 10 to the 3 to 10 to the 4 times brighter. And right now, the field is really moving towards characterizing them in detail. And so one key aspect of it is to measure their atmospheric compositions, because this will help provide clues on how these objects form. So this is because depending on how you form, you accrete different kind of material. And the two dominant formation scenarios for these giant planets and brown dwarfs are core accretion and direct gravitational collapse. So core accretion is a bottom-up process where you accrete solids and then undergo a runaway accretion of gas. Whereas in a direct gravitational collapse from either a molecular cloud or a circumstellar disk, you would inherit probably the composition of that cloud or disk. So by really measuring the things like the metallicity and the carbon to oxygen ratio of these objects, we can try to put constraints on how they formed. So specifically, I'm looking at the brown dwarf companion HD 4747b, which is an LT transition object, meaning that its spectral type is consistent with late L or early T. This is a transition that's been known to be caused by a decreasing temperature of the object. And objects in this transition also are found to be pretty cloudy. So HD 4747b is a very special target because we have decades of monitoring with Keck high-res, as well as years of NERC2 imaging for it. So combining these data as well as accelerations from the Gaia and Hipparcos astrometry missions, I was able to get a very precise dynamical mass for the object, as well as orbit. Previous studies using the low resolution spectra of the object also found that cloudy models fit its atmosphere best. And in addition, because of its high mass and relatively large orbital separation, we do expect this object to have formed via direct gravitational collapse. So we can check whether its atmospheric composition is consistent with its stars. So on the left here is an image of it after post-processing. So you can see it's about 9 magnitudes fainter than the star in K-band at a separation of only 0.6 arcseconds. So using Kpick, which JB has talked about yesterday, we can inject light from the companion into single mode fibers, which then get directed into Keck near spec. And using near spec, we can resolve the lines in the companion's atmosphere at high resolution. So this is what the data looks like after reduction on the left, where I'm showing the second half of K-band, roughly 2.3 to 2.5 microns. And so this data consists of companion light, as well as any leaked starlight that's also coming into the fibers and into near spec. So we have to model that as well. But if I just do a quick cross-correlation analysis of this data with a model brown dwarf template, we can detect carbon monoxide on the top right and water to high significance, and also at the expected radial velocity shift of the companion, given our knowledge of its orbit. This data is at high resolution, specifically resolving power of about 35,000. So we also complement this with low resolution data from the Gemini Planet Imager, or GPI, which is at a resolution of 50. This data covers a wider wavelength range from 1.5 to 2.2 microns. And you can see that unlike the high resolution data, here we can get an idea of the spectral shape, whereas the high resolution spectra can actually resolve individual absorption lines. So this is also very useful. And so I got data that was published in a 2015 study, but because of improvements in the pipeline and the data reduction procedure, I've actually re-extracted the spectra and got a much higher signal to noise. So this is shown in black here. And I'm comparing it to a L6 and a T0 dwarf. So these are brown dwarfs without host stars. These are isolated objects with relatively good spectra. And we can see that the spectral shape of HD 4747b does match them well. So with this data, I'm running a series of atmospheric retrievals where I'm using petite retrans as the radiative transfer tool. And I'm following mostly the setup in Mollier et al. 2020, which has been demonstrated on HR 8799E, which is another directly imaged planet. So a key aspect of this is I can use the mass of the companion that we know from its orbit fits as a prior, which helps a lot because the spectra usually doesn't constrain the mass well. And I want to fit the atmospheric abundance in terms of the C to O ratio and metallicity in order to compare with the stellar values. And because we don't know much about the clouds in these objects at all, I'm trying very different models, including a clear model without any clouds, a gray cloud deck where you have a thin layer of gray opaque clouds that block all emission underneath it, and a more physically motivated cloud model that considers the sedimentation and diffusion of cloud particles. And I'm specifically choosing instatite or MgSiO3 as the cloud species, as this has been found to be the most important species from previous studies. So here I'll talk a little bit about how we fit the high resolution spectra from NIRSpec, specifically with the Kpick mode. So from petite retrans, the previous tool I talked about, we can get a spectrum of the companion as shown in dark purple here. And I need also to model the star emission from the star. So for that, we have on-axis observations of the star with the same fiber and same setup. So we add up the companion and stellar contributions linearly to form the full model in orange. We also correct for the telluric absorption effects using observations of a standard star. So after running a series of fits with this data, I found that all the cloud models I tried give consistent values for the C to O ratio and the metallicity. So on the left here, on the right here, you can see in 3 colors are fitting results from the 3 different cloud models. And it's clear that the high resolution spectra is not very sensitive to the cloud assumptions at all. All the posteriors overlap significantly. We can compare the radius and radial velocity shift of the object with our prior expectations, and they match well. And the V sin I, or projected rotation rate of the object, is a new result from the study. And most importantly, we want to compare the C to O ratio and metallicity of the object with its star. So in this case, we see that the metallicity already matches pretty well, whereas the C to O ratio seems slightly higher. And so I'm still doing a detailed analysis and correction for this because previous studies have found that, in fact, you can expect that some of your oxygen is locked into solids, such as instatite, and those would not be seen by our data because we only probe the gaseous molecules, the carbon monoxide and the water and other molecules. So if we do this correction, we may be able to push the C to O ratio down a bit because in fact, you have more oxygen in the object's atmosphere than you can see. But right now it's looking pretty promising. So on the other hand, we found that the low resolution spectra are very sensitive to the model choices, especially the cloud assumptions. So we can see that on the left here, I'm plotting the GPy spectra in black and the 3 best fit models from the 3 cloud assumptions in color. So while they agree well at the GPy wavelength range, they disagree significantly at shorter wavelengths. And we can compare what the effective temperatures and radii these models are consistent with previous expectations. And we see that right now, the Insta-type cloud model actually fits prior expectations on the temperature and radius best. The temperature is expected to be around 1400 Kelvin, and the radius around 0.9 Jupiter radii. Whereas the other 2 models give radii that are too small and temperatures that are too big because these are degenerate parameters. However, we also find that the GPy low resolution data does not constrain the atmospheric composition well. So on the right in red here are the results from the GPy low res retrievals. And in blue are the high res near spec or Kpick retrievals. So clearly Kpick does a better job of measuring these parameters. So to summarize, I'll say that Kpick high resolution spectra can constrain the atmospheric composition well and much better than low res spectra. It is also relatively unaffected by any assumptions on clouds, which are a major unknown in this field. So this is very good because we can, in a sense, get around the problem of clouds. And finally, we have a survey of substellar companions underway with the Kpick team. And Kpick could probably measure compositions for many other brown dwarf companions, as well as directly image planets in the future. And this will enable statistical comparisons. So thank you, and I'll take any questions.
So you just repeat it when it.
Max.
Great talk, thank you. So here you point out that the constraining these properties
Yes, that's true. That's a good point. So the question is, it seems like the low resolution spectra constrains the radius better than the high resolution spectra. Yeah, and that's true because so the low resolution data does have some information that we want to add. So eventually we want to combine both types of data to do a joint fit between the high and low resolution data. But the low resolution data is flux calibrated. So this units on the y-axis on the left here are in physical units, which is why it constrains the radius and temperature better. Evan? Oh, yeah, that's a good point. Yes, so the question is the velocity shift of the object in wavelength space or velocity space large enough that we can be sure we're not measuring water from the Earth's atmosphere? The question is yes, because so if we look at this plot again, so if we look at our data and we, so the velocity shift of a water signal should be at 0. But if we look at the radial velocity here, it's not 0, and if you actually fit it, it's pretty significantly different from 0. So it's 15 plus or minus 0.4 kilometers per second, and given that we expect it to be about 15, it matches the orbit well. So we're pretty sure it's not Earth water.
Question in the Q&A.
Yes. Question is, do you have plans to model the host stars to get their Ceto ratio or metallicity? Yes, that's a great point because a key aspect of this is to compare the abundances with their host star. So this object has some prior constraints, which I'm showing in text here. Yeah, we are talking to some collaborators to do this kind of analysis on other stars as well, and maybe to repeat older analyses. That's a good point.
Well, let's thank Jerry again for a really nice talk.
Thank you.